Hello, my name is Ms. Smith. Today we're going to graph inequalities on the coordinate plane. Your learning target is, I can graph linear inequalities on the coordinate plane. In previous lessons, we graphed inequalities on the number line. Today we're going to graph them on a coordinate plane. You graphed linear equations in two variables already. When you graphed them, it made a line. Today, you're still going to be graphing that line, but you have to decide whether that line is solid or broken. When you graph a linear equation, all the points on that line are solutions to that equation. Well, today on an inequality, you have to decide whether or not the points on the line make the inequality true. So before we start, I'm going to do just a couple of examples. If I have y is less than x plus 1. My slope is 1, my y-intercept is 1. So I'm going to graph my y-intercept, and then I'm going to use my slope. So graphing a slope-intercept we've done before. First identify your slope and your y-intercept, graph your y-intercept, then use your slope as rise over run. I made this a dotted line, and I want to tell you why I did that. If you have less or greater, it's a dotted line because no point on the line will work in the inequality. If you have less than or equal to or greater than or equal to, it's a solid line because the equal to part makes it part of the solution set. But y is less than x plus 1, so no point on this line will actually work in that inequality, so I have to make sure that it is a dotted line. Then I have to decide whether I shade above or below the line. One way to do this is to use a test point. So I'm going to use 0, 0. I can definitely tell that 0, 0 is not on my line. X is 0 and y is 0. Plug it in. 0, 0 plus 1. 0 is less than 1. Now, if that point's true and I've graphed my line correctly, then everything on this side should also be true. Now, if this side's true, the other side should be false. Well, let's test the point. We've got negative 2, 2. X is negative 2 and y is 2. So 2 and negative 2 plus 1. So I say I'm plugging it into my inequality. 2 is less than negative 1. Well, that's false. Every point above that line should make a false statement. But this line is broken. It is not part of the solution set. If I graph y is greater than or equal to 2x plus 1, this one's going to be a solid line because y is greater than or equal to. The equal to means a solid line. Every point on the line will work. And then I have to decide whether I shade above or below. My slope is 2. My y-intercept is 1. I'll make my slope a fraction. So my y-intercept is 1, up 2 over 1, up 2 over 1. It is a solid line. Now you have to decide whether you shade above or below the line. I'm going to use a test point. Well, 0, 0, I'm going to test 0, 0. X and y are both 0. Zero is not greater than or equal to 1. That's a false statement, so instead of shading below the line, I shade above the line. Notice I'm shading a half plane. I either shade above or below the line, and I also had to determine whether the line was part of the solution set. In this case, the line is part of the solution set, and so is above the line. In the previous problem, the line was not part of the solution set because it was less, and I had to shade below. Every point below the line made it true. Now we're going to go over to the other page that you have in your package, page 24. You can pause and try example numbers 1, 2, and 3 by yourself, and then we're going to go over them. So resume the video when you're ready to begin. Okay, now I think we're ready to begin. So what we're going to do is we're going to graph this. The slope is 2, y-intercept is negative 1. What kind of line do we draw? Well, we draw a solid line. And why? Because the line is part of the solution set. If you have less than or equal to or greater than or equal to, it is going to be a solid line, meaning that the line is part of the solution set. So y-intercept's -1 up 2 over 1, and it is a solid line. Now I have to decide where the shade. Now if it's in slope-intercept, it's greater than, so I think I'm going to shade above. So I'm going to test the point, -1, 1. X is -1, y is 1. Now notice I labeled what my X was and I labeled what my Y is as well. One is greater than or equal to -3. That is true. So if that's true, everything on this side should be a solution. So you shade above. Now notice it was greater. Now when it's in slope-intercept form, you can go by that. You just got to be careful if it's not in slope-intercept form, going by greater above, less below, because if it's not in slope-intercept, that doesn't always work. Where do we shade? Above the line. Why? All points above the line are solutions to the inequalities. It makes the inequality true. Where do we find the solutions? In the shaded region and on the line. Two possible solutions, -1, 1, 1, 1. You could list a whole bunch of different ones, any of them from the shaded region. And ones that are not solutions, any from the part that is not shaded. Now if we look at example number 2, it's already written in slope-intercept form as well. So the slope is -3. I'm going to put it over 1. Y-intercept is 1. Now this line is broken or dotted. And the reason it's a dotted line is because no point on the line works. So points on the line are not part of the solution. So that makes a dotted line. This is less, so we're going to shade below. And the reason we shade below is all points below that line will make that inequality true. We can always test a point. -3, -2. -2 is less than 10, so that is true. So all the points below that line should be true. So we shade below because the points below the line make the inequality true. Where do the solutions lie? In the shaded region only this time. Not on the line. The line is not part of the solution set. You can choose any point from the shaded region as possible solutions. So -3, -2, -2, -2. There's a whole bunch more you could choose, any of them from the shaded region. Ones that are not solutions, any point on the line is not a solution, and any point in the part that's not shaded. So 3, 0, 4, 2, 0, 1, not a solution. Example number 3 is an inequality. Still has two variables, but it's not in slope-intercept form. So we're going to first write it in slope-intercept form by solving for y, and you solve an inequality the same way you solve an equation, except if you multiply or divide by a negative, then you would have to reverse the inequality symbol. So subtract 3x, 2y is less than or equal to -3x plus 8. Divide both sides by +2, so your inequality symbol does not change. Now, I'm putting that negative with the top. It can be with the top, the bottom, out to the front. But in a moment, we're going to use it as a slope, so I'm going to just write it with the top. My slope is -3 halves, so -3/2. My y-intercept is 4. Now, it's got equal to, so the line is part of the solution set, so it is a solid line. Why? Because all points on the line are part of the solution set. So all points on the line make the inequality true, therefore they are solutions. Where do we shade? We shade below. Now, when it's not in slope-intercept form, it's important that you use a test point, because there are times that inequality symbol will reverse. Now, if you remember to reverse it, if you put in slope-intercept, it would be okay. I'm going to test a point. If I put 0 in for x and 0 in for y, I get 0 plus 0 is less than 8. Well, 0 is less than or equal to 8. So that is a true statement. So I shade below the line. Now, I really need to keep this going all the way out. I'll shade below the line. And you shade below the line because below the line, all those points make the inequality true. So points below the line. So where are the solutions? They're in the shaded region and on the line. List two possible solutions. I can list any that are on the line or in the shaded region, and ones that are not solutions are points that are above the line. Now, in summary, solving or graphing a linear inequality, you first have to determine whether the line is solid or broken, or dotted or solid. If it's less than or greater than, it's a dotted line. If it's less than or equal to or greater than or equal to, it's a solid line. A solid line represents that the line is part of the solution set. A dotted line represents that it's the boundary line, but it's not part of the solution set. Then you have to decide whether you shade above or below. If the inequality is in slope-intercept form, you can use this table to help you. If it's less than, it'll be a dotted line, and you shade below. If it's less than or equal to, it's a solid line, and you shade below the line. If it's greater than, it's a dotted line, and you shade above. If it's greater than or equal to, it's a solid line, and you shade above. So your learning target today is I can graph linear inequalities in a coordinate plane. If you have any questions about this video, please ask your teacher.